Hey, so the end of chapter 10, 10.5 and 10.6 are very similar to each other. What you're going to be doing is you're going to be solving trigonometric functions, okay? 10.5 is going to focus in on the basics of solving, and then in 10.6, when we get to the next video, you're going to be doing solving again, but this time you might have half angles that you're dealing with and double angles that you're dealing with. So we'll talk more about that when we get into 10.6 when we deal with the half angle and the double angles. But for right now, in 10.5, we're going to focus in on solving regular trigonometry equations. Okay, so here I've kind of given you some tips and tricks. Um, you know, when we are solving these, the big goal is you're going to want to get the trigonometric function by itself. Okay, so if I have one trigonometric function like sine, then I need to get everything away from sine so that the last step, and generally the last step that you're going to be using for all this is inverse trig. Okay. So everything that we did in 10.4 is going to be pretty important for us in solving trigonometric equations. All right. So you want to isolate your trig function, and we like it when we only have one trig function to deal with. Okay. If you have two trig functions to deal with and you're trying to solve and use inverse trig, it's not really going to work out in the end. You want to make sure that you're dealing with only one trig function at a time. Okay. Other things that are going to be helpful: factoring the trigonometric functions. So you need to know how to factor. That's useful in here. Also, using the quadratic formula if factoring is not possible. And then sometimes we will even multiply by a trigonometric function to help us introduce the idea of squaring. Okay. So you'll see a little bit of this later on where we have to multiply by a trigonometric function to help us out, to get us information and stuff that we can use. Okay. All right. So other things. So those are tips to help you get through this, but you also got to be aware because if we're doing inverse trig functions, you need to make sure that they can be done, because you might end up with an answer that has a no solution because we can't do the inverse trig function. Okay, so remember the inverse trig function must be able to be performed. And also with that, make sure that you know the ranges of the inverse trig functions. Okay, where do the answers lie? All right, that's important information. And then other things to know and be cautious of is make sure that you remember the trigonometric function periods. Okay, make sure that you remember those periods. All right, so let's do some solving. So take, for instance, this one. And now make sure that you're also paying attention to the directions. Where before, when we generally performed the inverse trig, you kind of only had, one answer. Now it's going to be possible that when we perform this, you're going to have more than one answer. Okay. So because we are actually going to go over the period of 0 to 2 pi. And make sure you pay attention to this because they like to switch this around. Sometimes I like to keep it in radians, and sometimes they will switch it back to degrees. So it'll say 0 to 360. Notice that we include the 0, but we do not include the 2 pi or 360 as it would be over here. All right. So go ahead, pause the video, give this one a shot. Get the trig function by itself and then run inverse trig. That's all you got to do. And go. Okay. So we want to get sine theta by itself. That means we need to get this -1 out of here and this 2 out of here. Okay. Think of this as like a giant variable right here. Okay. Think of this as if it was written as 2x minus 1 equal to 0. How would you get x by itself? All right. That's the idea. Get this trig function sine by itself. So how do we get rid of a -1? Add 1. So that gives us 2 sine theta equal to 1. How do I get sine by itself? How do I get rid of this multiplication? Divide. So divide by 2, divide by 2. So sine theta equals 1/2. So in order to figure out what theta is, because that's what we're solving for, how do I get rid of sine? And just like what I told you, once we get that isolated trig function, we're going to be using inverse trig. Okay? So now that we have sine by itself, how do I get rid of the word sine? I do the inverse sine. So here's what's really cool. All I really want to know is, when is sine 1/2? Well, a couple things that you should check first. Again, we gotta make sure that this is possible. So if I go back to my identity notes that I've given you, okay, go down to the inverse right here. So sine's domain says you got to be between -1 and 1, and 1/2 is definitely between there. Okay, right here it tells you the quadrants to look in for your sine value. Now, when we do this, we're not going to have a negative sine angle. We want the actual positive angle that's in quadrant 4. So we don't have to worry about this information, but this information right here, 1 and 4, tells us where we can go on our trig chart to see where sine is a positive 1/2. Look, sine is a positive 1/2. So one of our answers is pi over 6. That's the quadrant 1 answer. And then we know that the other one happens in quadrant 4. Make my 6 a little better. So if we go up here and we scroll down, here is sine 1/2. It is sine, right? Positive 1/2. So it is 150 degrees. Okay? Should have been in quadrant 4. Well, oh no, I take that back. Yeah, that's right. It is 150. It's right here. There's your other one. So 5 pi over 6. It's actually not in quadrant 4. That was for something else, which we'll talk about later on. So positive 5 pi over 6, if I remember right. So going back and looking here at this, there's the positive 1/2, 5 pi over 6. There you go. So that's what we know so far as the answers. And again, that's all you got to do. Once you got this done, make sure that this can happen by looking at your chart over here. Gosh darn you. Right there. So our answer is either in quadrant 1 or quadrant 4. So we found our answers in quadrant 1 because in quadrant 4, that's the negative version of the answer. Okay. So quadrant 1 or quadrant 4. And then make sure that you check out the rest of your chart to find the other guy, because there really are 2 of these. Here's another place where sine is a positive 1/2 at 5 pi over 6, or 150 degrees. Okay? And I'll explain, and I'm going to talk about that information when I get to the very last problem that we do. Okay? I'll explain why these 2 are the only answers. And that's it. That's what you put into the blank. Okay? So go ahead and try this one. Again, your solutions should be in radians. Pause the video and go. All right. So we want cotangent x by itself. So how do I get rid of plus 1? Subtract 1. So that gives us 4 cotangent x equal to 4. Then how do I get rid of multiplication? Divide. Divide by 4. Divide by 4. So cotangent x is equal to 1. How do I get the x by itself? Inverse trig. So we want cotangent inverse, cotangent inverse. Now, we got to make sure that we can do this. So go to your, oops, wrong notes. This one. So cotangent says, yeah, we can do it because we can use any number in here. All reals is the domain. Cool. So we now know our answers either in 1 or 2. Okay. So let's look in quadrant 1 and quadrant 2. So that's everything from 0 to 180. We need where cotangent is a 1. So right there, it's in quadrant 1. That's our answer. Quadrant 1, which is pi over 4. So x is equal to pi over 4. And that's the only answer, because if you go back and look, there are no other places where cotangent is a positive 1. See, that's 1 right there. Pi over 4. That's negative 1. Sorry, I stand corrected. Gosh, I am not doing well today. So there's also one other answer. At 5 pi over 4. I was thinking of a quadrantal angle. That's where I was messing myself up. So 5 pi over 4 is the other one. Okay? That was my fault. I apologize for that. And I'm sure some of you are probably like, Mr. Armstrong, you're wrong. 5 pi over 4. There we go. That's a better answer. Because again, and I should have just checked this, you're just looking at your cotangent and finding your other angle. And again, I will explain why these two are neat. Actually, you know what? I'm going to explain it now. Let's talk about why this is true. So right here, it tells us where our answer is going to be. It's either in quadrant 1 or quadrant 4. Or, sorry, quadrant 1 or quadrant 2. Okay? Now, with that being said, remember that there are 2 places where, in this case, cotangent is positive. Okay? So that's what you got to think about here. So let me explain why this is having 2 answers. Okay? There are 2 places where cotangent is positive. Remember, we got that phrasing, all students take calculus. Right here in this one, and I made everybody else capital letters. Why didn't I just do that? That's fine. Capital. A, which is quadrant 1, and right here with the T as in take, which means tangent and its reciprocal cotangent, these are the 2 quadrants where they are positive. Since we know the first guy, we can get the third one by treating this like a reference angle. Okay? So pi over 4 is my reference angle. I can find this angle in here by taking the reference angle, or sorry, by taking pi plus my reference angle. So if I take pi plus pi over 4, that gives me 5 pi over 4. Or in other words, 45 plus 180 gives you the 225. So this other guy, this other angle is based off of using your reference angle where this happens again based off of its sign. Okay? So if you're looking at the other ones, if you are looking for quadrant 4, you would basically take 360 degrees or 2 pi minus the reference angle. And if you want to get sines in quadrant 2, you would take pi minus the reference angle. Okay? So that's how we find the other one. That's another way that you can find the other one based off of what you know. This is positive, so that means cotangent is positive in quadrant 1 and quadrant 3. This is the reference angle. To find the other guy, all I got to do is take pi plus the reference angle. Okay? Oops, I don't know why I wrote reference there. Pi plus the reference angle to get the second angle. That works. Okay? So if we go back and look at this guy right here, we want to know when is sine positive. Well, sine is positive in quadrant 1, and sine is positive in quadrant 2, because that's what the S stands for. And again, based off of what I told you, take pi minus the reference angle to get quadrant 2's. And we already know that that is the reference angle, because that's in quadrant 1. So if I take pi minus pi over 6, that gives you the 5 pi over 6. That's where the second angle came from. Okay? Yeah, it's all about using the reference angle and the sign that you're looking at to find the other angle, because there are two positions in a circle where sine is positive. Quadrant 1, quadrant 2. There are two positions. Gosh, it skips over stuff. There are two places in a 360-degree rotation where cotangent, is positive. Quadrant 1, quadrant 3. Okay? All right. Go ahead and, well, actually, no, don't pause the video on this one. Let's talk about this one. Now, notice that you have more than one piece of information to deal with. Okay? So you've got cosine and you've got cosecant. Now, you can try changing this into something else. It ain't going to work. All right? You could try changing this into 1 over sine x and then multiply everybody by sine. It's not the idea that's going on here. That's not what they want you to do. Okay? So, in this one, remember how I told you that we want to isolate the trig function, and we're going to do that. Okay? But the problem is I got two trig functions. So generally when there are two trig functions, I'm going to look to these last three. Okay? Maybe there's some factoring that can happen, or the quadratic formula. Okay? Now remember, in order to do factoring in the quadratic formula, what do you have to make sure happens first? That's right. You have to be set equal to 0. So I'm going to take this 2 cosine x, and I'm going to subtract it to the other side. Minus 2 cosine x. So what I have now is the square root of 2 cosine x cosecant x minus 2 cosine x equal to 0. These two don't get together, because think of these, again, think of this kind of like if we're in terms of variables. This looks like square root of 2xy minus 2x, where x represents cosine and the y represents the cosecant. See, we can't put those two together. It's not like terms. All right? But if you kind of look at it like this, since we're equal to 0, I can't use the quadratic formula because I don't have anything squared. But what do you notice between these two? What do both of these share in common? Oh, they both have an x. Factoring says that if I have something in common in both of these, that's called a GCF, and I can pull GCFs out. Look up here. Both of these have cosine x. So I can pull that out like a GCF. Pull out cosine x. What does that leave us with? Square root of 2 cosecant x minus 2 equal to 0. Now this is something we can work with. Sorry, I like to coordinate things a little bit better. Remember that once everything was factored, so this is as far as what factoring can go for us. How do we solve? Well, remember we just take each piece and we set it equal to 0. So we can take cosine x, set it equal to 0. Okay, we could take this factored piece. So we're just taking each factored piece and we're going to set it equal to 0. That's called the zero product rule. Now that I've done a little bit of factoring and I set these equal to 0, can I solve each one of these? Yeah, absolutely. There's only one trig function here. There's only one trig function here. You can solve that. We're right back to what we just did in these problems right here that I first started you out with. Okay? So, how do I get x by itself? I'm going to take the inverse cosine of both sides. So x over here only happens when cosine is 0. When is cosine equal to 0? Again, just to double check. Cosine, yes, we can do it because we can have cosine equal to 0 in here. All right. So we can figure that out. So we go to our big chart and we look up when is cosine 0. So let's just follow all the way through. So right there. So pi over 2. And actually, how does it want our answers? That's a good question. Still wants it in radians. So pi over 2. Now, is there any other place where cosine is 0? Scroll down. I think there might be one other place. Come on, you. So cosine 0, there it is, right here at 3 pi over 2. Okay. Okay. And these are quadrantal angles, which makes sense because if you're thinking about these in terms of like unit points, this is 0, comma, a positive y. And this is 0, comma, negative y. And cosine is all about the x value. So what are the x values for both of these? Zeros. And so when you're up here, this is pi over 2. And when you're down below, that's 3 pi over 2. Okay? So over here, solving this guy. So we're going to add 2, which gives us the square root of 2 cosecant x equal to 2. And then we're going to divide by the square root of 2. So cosecant x is equal to, now remember, we do not like radicals in the bottom, so you got to rationalize. Square root of 2, square root of 2. So when all is said and done, you end with the square root of 2. So we want to know, when is cosecant x equal to the square root of 2? Well, again, we got to know, can we do that? So cosecant only works if we are above 1 or below -1. So we need to know, is the square root of 2 above 1 or below the -1? And it's definitely above 1. So we can do this. So we go to our table, and we're going to look at cosecant. So right down here, we want to know when we are the square root of 2. So there's one of them, pi over 4. And then the other one should be another one. There it is, at 3 pi over 4. So we now know that this x is equal to pi over 4 and 3 pi over 4. And again, that makes sense because this is all about when cosecant is positive. When is cosecant positive? In quadrant 1, because everybody's positive, and in quadrant 2, because cosecant is the reciprocal of sine. Okay? So that makes sense. So there's your answers. You actually have 4. Pi over 2, 3 pi over 2, and pi over 4, and 3 pi over 4. Again, just like all the other equations that you've done before in algebra, you can always plug these answers in and see if they work. So you plug in the pi over 2, pi over 2, pi over 2, and you can check it. You can plug in the pi over 4, pi over 4, pi over 4, and you can check it. So you can always check these answers to see if they are actually indeed working for you. Okay? All right. Try this one and go. Okay. So hopefully when you saw this, the first thing you thought of is, oh, there's a GCF up here. 8, 16, and 8. So I'm going to pull out 8 and deal with sine squared x plus 2 sine x plus 1. And hopefully when you were looking at this, you're like, oh, I know what's going to happen on this. Hopefully you're like, I'm going to factor on this. Because if I think of sine as just the variable x, I've got x squared plus 2x plus 1. You could either factor that or run the quadratic formula on it. Your call. Okay? So you could either factor that or run the quadratic formula on it. It's your call on what to do. All right? So I just factor it. And if you factor this guy, sorry, I was trying to erase here. This is what it's going to factor out to. So this thing will factor to 8, because that's your GCF we pulled out, sine x plus 1, and sine x plus 1. Because if I take sine times sine, I get sine squared. If I take sine times 1, I get 1 sine. If I take 1 times sine, I get 1 sine. And 1 sine plus 1 sine equals 2 sine. And 1 times 1 is 1. See? Foils out. And now, can I solve this? Absolutely. Just like what we did last time. Take each part, set it equal to 0. So 8 gets set equal to 0, but does that make any sense? No. 8 equal to 0, this is just junk. And then sine x plus 1 equal to 0. I don't have to do both of them because they're both going to end up being the same answer as whatever this guy comes out to. So don't worry about doing both of them. Okay? So if we solve, if we get sine by itself, because we can do that now, subtract 1, subtract 1, sine x equals -1. And if you ran the quadratic formula, you would have found that was the answer, -1. So then you just take and you set sine equal to -1 because that's our trig function. Okay? How do I get sine by itself? Inverse trig. Sine inverse, sine inverse. And can we do that? Yes, we can. It's part of our domain. And so we just need to go through to our chart and find when sine is -1. So sine is this first column here. So where is sine -1? There we go, right here. Sine is -1 at 3 pi over 2. I don't think there's any other. Just double checking. Nope, that's it. 3 pi over 2. So sometimes it's okay, and you will end up with only one answer. 3 pi over 2. And it did want it in radians, right? Yeah. There we go. Okay. All right. So let us continue on. All right. So let's talk about this one. Okay. This is where we're going to use that feature I talked about back at the beginning. Sometimes we need to multiply by a trig function. Okay? Because this will help us introduce squaring, but also it's going to help us do something else. So if I go back to this, okay? Oops, thought I was on the eraser for a second. There we go. There's a relationship between sine and cosecant. Remember that cosecant is 1 over sine. So that's good to know. So if I was going to multiply this by a trig function, what trig function should I multiply this by? And hopefully you're thinking, well, since this is the denominator and I don't like to work with fractions, let's multiply everybody by sine. And that's exactly what you need to do. Step 1, we're going to take this entire thing times sine x. Because it's going to introduce squaring for us, but it's also going to cancel this guy out. Because we don't like fractions. We don't want a trig function in the denominator. So let's multiply. So this is going to give me 2 sine squared x. Then I'm going to come over here and multiply this one. And that's going to give me 2 minus the square root of 2 sine x equal to, and then if I come over here and multiply that guy, remember sine times cosecant will just cancel itself out, leaving you with the square root of 2. Hopefully now you see something that you can do with this. Oh my gosh, I can factor this. And that's exactly what I want you to do. Go ahead, pause the video, continue, and do the factoring for this. Be careful with your factoring. And also remember that you need to be equal to 0 in order to factor. And go. Okay. So the factoring for this and the solving. So we're going to move this square root of 2 over first. We got to do that because we have to be equal to 0. So that's going to give us 2 sine squared x plus parenthesis 2 minus the square root of 2 sine x, and then all the way down here, a minus the square root of 2 equal to 0. All right. So, first things first. Basically, what this is going to be, it's going to be a lot of trial and error because you got to pay attention to the front. And you got to pay attention to, sorry, I was about to circle the 0, the back piece. So, we need the factors of 2. Well, that's 1 and 2. That's easy. We need the factors of the square root of 2? Well, that's easy again. 1 and the square root of 2. So our equation is going to factor somehow with the numbers 1 and 2 and 1 and negative, or 1 and square root of 2. Now also notice that we need to make this in part negative. So that means one of our parentheses is a positive, one of them is a negative. We also know that sine x has to go here in the first pot because we need sine times sine to be sine squared. So all we're going to do is we're going to fill in those numbers here with either 1 or a 2. And then we're going to fill in these numbers with either a 1 or a square root of 2. Okay? So it's trial and error. So let's say we've got 1. And let's say we put the 2 here. And then let's say we put the other 1. And then the square root of 2 here. Let's see if this factors out correctly. So 1 times 2 is 2. Sine times sine is sine squared. Okay, that works. So 1 times negative square root, or 1 sine times negative square root of 2 gives us a negative square root of sine. Okay, that's, or 2 sine. 1 times 2 gives us the 2 and a sine. So yeah, that's working out because you'll have negative square root of 2 sine x plus 2 sine x. And if I pull the sine out as a GCF, what's that going to leave me with? A negative square root of 2 and a positive 2. So 2 minus square root of 2. So that checks. And then what's 1 times a negative square root of 2? Hey, negative square root of 2. So it worked. So it's just trial and error. If that didn't work, then I would have maybe just come in here and taken the 2. Oops. Come in here and grabbed the 2 and switched it with the 1. Excuse me, and see if that would have worked. Okay, it's just about playing around, switching numbers around. But that worked, though. That actually gave us what we wanted. And now that we have it factored, we can solve. Okay, because all we're going to do is take these pieces and set them equal to 0. I'm not going to put the 1 in front of this sine. So sine x plus 1 equals 0. And then over here you have 2 sine x minus the square root of 2 equal to 0. And these can be solved. Okay? So let's do some quick solving. So this first one right here, all we're going to do is subtract 1, sine x is equal to negative 1, which means we do inverse sine. Sine inverse, sine inverse. So x is equal to, we want to know when is sine negative 1, and we've done that before. I think we just did it on the previous one. Yeah, when is sine negative 1? And that was 3 pi over 2. All right, so there's part of our answer. This guy right here is 3 pi over 2. Okay? The next one, we're going to come in here and add the square root of 2. And that gives us 2 sine x equal to the square root of 2. And then we're going to divide by 2. So sine x equals square root of 2 over 2. And we will run inverse sine on this one. Sine -1, sine -1. So x is equal to, we want to know when is sine the square root of 2 over 2. And if we check this, square root of 2 over 2 is within this domain. Okay? So we go to the trigonometric chart, and we want to look, when is sine the square root of 2 over 2? So there's one, 3 pi over 4. And there should be another one, pi over 4. There we go. Pi over 4 and 3 pi over 4. And there's your answers. There are 3 this time. Little bit of algebraic factoring going on there. Your algebra skills got to be strong in here. Okay? But it was just a factoring problem. Once we multiplied. Okay? Introduced some squaring for us. And it also got rid of this guy over here because it's basically canceling out the fraction. Okay? Clearing the fraction for us. All right. There's only 2 more problems left. So this one wants all exact solutions. All exact solutions. And I don't know why I don't have the piece for this. Well, actually, this is a multiple choice one. You're not actually filling in the blank. So all exact solutions. And this one, they're dealing with this as degrees, looking at the problem. Okay. So what are all the exact solutions in degrees? All right. So subtract 1 minus 1 sine theta equals -1. So when I solve this, if I do inverse sine, we want to know when is sine -1. So theta is equal to, and we already know the answer to this, should be 3 pi over 2 because we've done it right here. See? When is sine -1? 3 pi over 2. We also did it on the previous example before that. So this answer is 3 pi over 2. But that's only one angle. Okay? What is the period of sine? This is why I put that beware in there. What is the period of sine? The period of sine is 2 pi. Okay? So if I want all exact solutions for this, I need every time this angle happens over and over and over again over 2 pi, over 2 pi, over 2 pi. Or in other words, we're talking about coterminal. Okay? But it's not always coterminal because if you remember the period of tangent only happens between 0 and pi. So that's why I put you in this warning right up here. Make sure that you know the trigonometric function periods. Okay? That's super important. Ooh, not that guy. So, give me all the angles that are going to be coterminal to this. Well, that would be plus 2n pi, where n is an integer. There we go. Okay? So this gives me all the coterminal angles. Or most of the time when I write this, I usually say, instead of 2n pi, sometimes I call it n times 2 pi, where the n is how many times we're either going in the positive direction. It's still an integer. So if I had like a positive 2, that means we go 2 times in the counterclockwise direction, 2 pi. Okay, 2 spins. If I said negative 2 here, then that means we'd be going clockwise 2 pi. Or in other words, 2 spins clockwise for the negative 2. All right. So this is, again, just talking about coterminal. That's all this is about. Coterminal angles for all right here. Okay. And we use 2 pi because that's how long it takes for sine to happen. Okay. All right. So let's take a look at another one. Just so you know, if this was tangent, the period for tangent is pi before it starts to repeat itself. Okay? The period for tangent is pi. So if I was to write this up, if this was according to tangent, it'd be 3 pi over 2 plus n pi. Because tangent only happens in a period of pi. All right? So that's why I'm saying it's important to know your excuse me, to know your periods. All right, last one. So between this one's factoring and this one right here, these are your two hardest problems you're going to see on your assignment. Okay. So obviously you can see in this one, it's going to take, you're going to think factoring, but the problem is this is not factorable. So when it's not factorable, I need you to revert to the quadratic formula. Okay. So this is one of those problems where we need to use a quadratic formula, and think about it like this. This is 7x squared minus x minus 2. So now you know your real A, B, and C. And just think of that x is really just sine x. So instead of saying sine x up here, I just called it x. I replace it like what you've seen me do before. So your A is 7, your B is -1, your C is -2. I want you to go ahead, pause the video, run the quadratic formula on this. Go. Okay. So if you ran your quadratic formula, this is everything that should have happened. So B squared minus 4AC. I always like to run the discriminant first. So that's -1 squared minus 4 times your A is 7. Your C is a -2. Okay. Reason why I run the discriminant first, because if this is negative, I stop right here because we only care about real solutions. And a negative number here would mean that you would have complex solutions. So this is 1 minus 4 times 7 times -2 gives us -56. This is because of the subtraction. This is because of the number that's all right here that I multiplied. And a negative by a negative is a positive. So that gives us 57. So now when I run the rest of the quadratic formula, it says x equals the opposite of b plus or minus square root b squared minus 4ac, but we already know that number. That's what we found right there. All over 2a. So x is equal to, the opposite of a -1 is a +1, plus or minus square root of 57 all over 2 times a, which is 7. So if we run everything out, x equals plus or minus square root of 57 all over 14. Now what we need to do is we need to go to our calculator and we need to let it run this information. One time where we do 1 plus the square root of 57, and we'll run it again where we do 1 minus. And remember that this is x equals, or in other words for us, it's sine x equals sine x equals. Okay? So we're going to go to the calculator. Alpha y equals, because it's a fraction, 1 plus second square root, 57, all over 14. So there's one of our answers. And we want as many decimals as possible because we need to be exact. We're not rounding until the very, very end. And there is rounding on this one because it's not an exact answer. So we've got 0.61070. So 0.61070 and 24597. 24597. Okay? And then we do it again, but instead of the addition, we have subtraction. So there we got negative 0.46784. 46784. So negative 0.46784. Okay. And the rest of the number is 53168. 53168. 53168. Okay. So there's our two numbers. There's what the quadratic gave us. So how do I get x by itself? Inverse sine. So sine negative 1, sine negative 1, sine negative 1, sine negative 1. Okay? And up here, again, it wants all exact solutions. They're going to want you to keep this in radians on this problem. I know that for a fact. So you're going to be staying in radians. I did everything in radians, but it's not hard to make stuff in degrees. There will be some degrees on there. All right. So x equals. Okay. So we go back to this and double check these. Can we run the inverse on these? And yes, this guy is between negative 1 and 1. This is between negative 1 and 1, which is what it says it has to happen. Okay? You can't go to your chart to do this because none of those values are on there. So again, this is where we got to rely on our calculator. So we're going to run second sine, and I'm going to go up and I'm going to grab that number. Now that's in degrees. I want to be in radians, so I should have checked that beforehand. So I'm going to scroll down, radians, and I'm just going to rerun that. There's my number in radians. So one of my angles is 0.656947. And wrong one. 6947 3885. 3885. Okay? Now, let's explore this. So remember how we were talking about that there are two angles. This is where all that information that I shared with you on those first three problems comes into play. We are looking when sine is positive. Okay? When is sine positive? Well, it's positive in quadrant 1, because that's all, and it's positive in quadrant 2. The question is this the reference angle? That's what we want to know. Okay? So, is this the reference angle? And then, in fact, it is. This is the reference angle. How do I know that? Because this number is smaller than pi over 2. If you take pi divided by 2 in your calculator, this is how you're going to know that's the quadrant 1 and not the quadrant 2 answer. Pi over 2 is 1.57. Blah, 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 blah. If I go back to this, 0.65 is less than 1.57. So that means this number right here is over in quadrant 1. So I've already told you how to find the quadrant 2 angle. All we have to do is take pi minus 0.6569473885. And so if you just go to your calculator and do select pi minus, scroll up and grab that number. So you don't have to do a lot of re-entering. And there you go. There's the other angle that's in quadrant 2. Okay? So 2.4846. 2.4846. 4526. 4526. And 5. Okay. We'll talk about how we get the answers because, again, this thing wants all exact solutions. Okay? So over here, once we find x, so we're going to go to the calculator. Second sine. Go up there, grab that negative 4.6 right there. Close it, enter. So there's our value. Negative 0.4868. 48685125. And a 3. Now, and then in this one, we want to know when is sine negative. So sine is negative in quadrant 4 because only cosine and secant are positive. And sine is negative in quadrant 3 because only tangent and cotangent are positive. Now the question is, which one is this? Well, the problem is that they have given us this answer according to sine's range as the negative value. So this is an answer that is in quadrant 4. Okay? But I need the real quadrant 4 value, as in between 0 and 2 pi. So the first thing we need to do is we need to take that negative angle And we need to find the real answer that goes right there. Okay? So we're going to take negative 0.48685125 3, and we're going to add 2 pi onto it. We're going to go coterminal. Okay? And so our quadrant 4 angle will be taking that number right there, adding 2 pi. There's our quadrant 4 angle. 5.7963. We'll put that up here. 5.7963. Wrong one. 3405. I believe that last number was 4. Yeah, 4. So that's the real answer we want there. All right. Now, we need to find quadrant 3's answer. So in order to do that, all you're going to do is remember we're going to take pi plus the reference angle. Here's a cool fact. This guy right here, that is the reference angle because this is moving negative degrees this way. Okay, this is the reference angle, just knock off the negative. So if I want to figure out this information over here, all I got to do is take pi plus that number that's right there. Okay, other than it knock off the negative because that will be the reference angle. Because if you really wanted to find the reference angle here, you would take 2 pi minus your angle in quadrant 4, which is that guy. And if I take 2 pi minus that angle, I get the positive version of that, just so you know. That's to help you find the reference angle. All right. So then let's do this. So to find my last guy, I'm going to take 2. Sorry, not 2 pi. Pi. Just pi. And I'm going to add my reference angle of 0.48651253. So I'm going to go to my calculator and I'm going to take pi plus, I'm going to go up there and grab my angle. And all I'm going to do over here, oops, I got a little bit of extra information I don't really need. Just delete that stuff off. I'm going to go over here and delete that negative sign. And there's that reference angle that I was talking about. And there's the other angle, 3.62844. 3.62844 3907. All right. Now we have all our angles. All we want to do now is make our equations exact solutions. And they rounded all of these to 4 decimal places, just so you know. So now, if I go back, starting with just quadrant 1, because I like to work in quadrant 1 first. So if I round this to 4 decimal places, that's 0.6569. So 0.6569. to get all the angles that'll work for this, it'll be plus 2n pi. I don't know why I put pi first when I said n. Because again, the period for sine is 2 pi. And we just want to keep going around and around and around at this angle. So there's your quadrant 1 angle. Quadrant 2, here is that value. So we'll take 2.4846 plus 2n pi. Quadrant 3, we figured out right here in purple. So that'll be 3.6284 plus 2n pi. And then last but not least will be the 5.7963. 5.7963 plus 2n pi. And that is what they are looking for your answers. Because these first four right here solve the problem, and then this piece right there gives you all the other answers that will work if we keep going around coterminally. I know that was a lot. Again, you know, this is like the last problem in that assignment, you know, between this one and the factoring you do on this one. I think those are your two most difficult problems. Okay. Other than that, that's 10.5. And 10.6, we're going to apply the same information, but we're going to do double angle and half angle formulas along with them. So with that being said, thank you for playing and catch you next time.